nucleus. So good afternoon or good morning, everybody, depending on where we are. Today, I'll tell you about how we can learn about important questions in physics by studying the cosmic explosions where compact objects, so neutron stars and black holes, are born. Right. So the two images in the background you see, I hope that you're seeing my screen well, are on the left. The first, the neutrons are murdered detected in both gravitational waves and electromagnetic waves, so GW17 or A17. And on the right is the first confirmed disappearance of a massive star without a standard supernova, which we think indicates the formation of a black hole, a failed supernova. So the plan of the talk is first to give you a broad overview of these explosive transients associated with compact object formation. And then I'm going to talk about the work that I've been carrying out in my research group over the last few years. And I've been told that people here know what a neutron star is, and so I probably don't have to explain that. But I'll just give a very brief refresher of, massive star evolution, compact object formation, and supernova, so that we kind of remind ourselves of all these things. So of course, we all know the sun is powered by nuclear reactions, burning hydrogen at the center through fusion, but stellar evolution by now is a well mature theory, and so we know that stars like the sun will end their life as a white dwarf. But stars more massive than about 8 solar masses are hot enough at their centers that they can burn heavier elements, and in particular, they can get beyond carbon burning. Okay, and if they're more massive than about 11 solar masses, all advanced nuclear stages take place, which culminate with the formation of an onion shell-like structure in which increasingly heavier elements are burned until an iron core is formed. And we all know that iron is the most tightly bound element that comes in large abundances. There's one that's even more tightly bound, but the abundance this time is like nickel 62 or something like that. But iron 56 is very close to that. So we can say that it's the most tightly bound element produced in large amounts, and so no more energy can be extracted by nuclear fusion. So the core is supported by electron degeneracy pressure, grows in mass because the silicon shell just outside of it keeps burning, so it's dumping ashes. And an object supported by electron degeneracy pressure eventually becomes unstable when the mass grows large enough. In addition to the Chandrasekhar mass concept, there's also a photodissociation of heavy nuclei because of the high temperatures, and so that also removes thermal energy, and eventually the core collapses on a dynamical time of about a second or so. Eventually, the central regions reach nuclear saturation density, at which point the strong nuclear force becomes repulsive. Once you start squeezing nuclear over distances shorter than about a nuclear radius, 10 to the minus 15 meters. And so it becomes repulsive, and so a hard, stiffened core forms, and this is what will become a proto-neutron star. This, of course, for stars less massive than about 100 solar masses, 140 solar masses. Stars more massive than that undergo a separate instability called the pair instability supernova. But those stars are not very abundant. The vast majority of massive stars will undergo this evolutionary mechanism. So you have this hard, stiffened core that's going to become a proto-neutron star, but it is relatively hot in the sense that the thermal energy KT is not so small compared to the degeneracy energy. Right? So the thermal corrections to the pressure are still important compared to, let's say, a cold neutron star that has cooled down over millions of years. And the temperature, 10 MeV or so, is such that significant neutrinos are emitted, both from the interior of the proto-neutron star and the accretion flow that's adding material to this proto-neutron star. And the formation of this hard core results in a bounce pulse that eventually becomes a shock that makes its way out. It stalls because it loses significant energy, and the current, the mainstream explosion mechanism for this Corcola supernova relies on some of these neutrinos that are being emitted from the central neutron star being absorbed in a layer just behind this shock wave. Okay, and that energy deposition pushes the shock, that basically results in a thermal expansion of the shock, and eventually the star explodes. Okay, that's the standard neutrino mechanism. There are other ways to blow up the star. For example, if there's rapid rotation, rapid meaning that the rotation rate becomes a non-negligible fraction of the Keplerian frequency, and then we can have something called the magnetorotational mechanism, which magnetic fields are amplified, and you have a broad collimated outflow exploding the star. And there's another mechanism that is more speculative, but it's not dead yet, and has to do with a possible phase transition at the center of the neutron star from normal neutron, proton, electron, muon matter into deconfined quark matter, so the quark phase transition, and that lowers the adiabatic index below 4/3, and there's a second collapse at the center of the neutron star, and a second shock that goes out and joins the first shock and explodes the supernova. But again, that depends on a certain nuclear physics parameters. But it's another alternative mechanism. But the mainstream mechanism is the neutrino mechanism, as far as we know. Now, generally speaking, there are many cases in astrophysics where one has a blast wave going out. It can be a Corcola supernova, it can be a type 1a supernova, also neutron star mergers. We have this situation. We have a blast wave going out that it has thermal energy, but is opaque to photons. Okay? And eventually it becomes transparent enough that the thermal radiation can leave the object, and we have a transient that peaks on a time scale such that the expansion time is equal to the radiation diffusion time. Okay, that's characteristic peak time for such a transient. And in the case of supernovae, there is an internal energy source that persists after this initial thermal energy caused a peak in emission, this radioactive heating for the most part, and so that allows the transient to continue shining following the radioactive decay time dependence. In the case of neutron star mergers, we have the R process that generates a power law energy deposition, and also after the first transient expansion peak, there's a power law dependence of the transient. Okay, it's a nice video from the Lawrence Berkeley lab. This is actually a type 1a supernova, but it serves to explain the concept. So supernova can briefly become as bright as their host galaxies. Right? This happens when this blast wave reaches the surface of the star, so the photons can emerge. Right? And so there's a peak in brightness, and then the subsequent evolution follows this radioactive energy deposition. And so we have spectra that change with time, and with the spectral length tells us the expansion velocity and so on. And this is a well-developed field, as most of you know. Now we have evidence for this neutrino mechanism I told you about in supernova 1987A, which, by the way, yesterday was, reached 35 years. So it was February 23rd, 1987 when it went off, right? So yesterday was the 35th anniversary of supernova 87A. And so there was a supernova observed. We had archival images in the Large Magellanic Cloud, so we know what the host star was. It was a blue supergiant, massive star. And we saw neutrino emission prior to the onset of the supernova, right? And the time delay between the neutrinos and the actual electromagnetic display tells us about the shock crossing time from the core to the surface. Right? So this is evidence for this picture of neutrino driven explosion of massive stars.
Here I have a naive question. So do you know, back in 1987, was this star even like within possible supernova candidates, or it really hit us by surprise?
As far as I know, it was a surprise. Even in fact, the neutrino people went backward to look for signals, and they found it retroactively once the supernova was found.
Yeah.
And so once people saw the transient, they say, oh, it's in the Large Magellanic Cloud. Maybe we have archival images. And so they went back and they found it. But I don't think they had a transient survey like the ones we have now, in which they're taking images every now and then. And so it's all a machinery in place. I think at the day it was quite different. I don't even know if they had the computational infrastructure, right? Nowadays they do what they call difference imaging, that you have a CCD image and they take a difference and say, oh, there's a little change. I don't know even if it was widespread at the time. Okay. So yeah, but I don't know the whole details. Okay, so we can learn quite a bit by studying about physics, by studying Corcola Supernova, so nuclear synthesis, the origin of heavy elements. The conditions in these explosions are such that pure neutrons and protons recombine first into alpha particles and then into heavier nuclei, and those heavier nuclei, as they move out, are spread out in the vicinity of the supernova, so they enrich the ISM with heavy elements. We can learn about the properties of dense matter, so the equation of state, so pressure versus density, temperature, and composition of neutron star matter cannot be tested in the lab because all we can do on Earth is look at nuclei at saturation density, but neutron stars reach densities higher than saturation density, so we cannot study them in the lab. So we can make predictions and compare with observations. We can learn about neutrino physics, particular neutrino flavor transformation, let's say any possible extra neutrino species and so on. That would have an effect on the energy deposition that's available to power the supernova. And also matter under strong curvature and magnetic fields. So here we're talking about general relativity and the fact that even though proton-neutron stars and Corcola supernova are not highly relativistic objects like neutron star mergers or black hole mergers, general relativity is still important in setting the detailed emission properties. And in particular, let's say a supernova goes off in the galaxy now, right? We have in place capabilities to make precision measurements. So we would have, I don't know, 10,000 neutrinos nowadays instead of 20, which is what was obtained for supernova 87A. We would have 10,000 neutrinos. And so the level of precision that those observables give us are such that general relativity has to be included if one wants to make precise diagnostics. Okay? And so this falls under multi-messenger astronomy, obviously because we have gravitational waves, neutrinos, and light, if, of course, one such supernova explodes close enough that we can detect it with all these instruments. Now, what I told you before is single star evolution. So what happens to a single massive stars, but we know that most massive stars, not most, at least half or even 70%, I forgot exactly what the number was, it's a paper a few years ago, more than half of massive stars that make supernova are in binary systems. Right? So then the evolution is slightly more complex than in single stars because there can be mass transfer. One or both of the supernova can unbind the binary system, right? Depending on how much mass is ejected, the energy of the explosion. If the explosion is asymmetric, it is expected that most explosions are asymmetric, and so there's a momentum kick. All these things determine whether the binary stays together or not. If a number of conditions are met, it is possible that the two massive stars undergo a supernova, and the remnant black hole or neutron star remain together. I'm going to talk about failed supernova that make black holes later, so I just told you about proto-neutron stars, but if you add sufficient mass to a neutron star, it's going to become a black hole. That's the short answer, right? Okay, so you can have, if the conditions are met, you can have a binary of two black holes or two neutron stars and a neutron star and a black hole, right? Out of two massive stars in a binary system. Right? Prior to 2015, binary black holes were thought to be a theoretical object with theoretical prediction, but as we all know, LIGO detected gravitational waves from a binary black hole in 2014, announced in 2015. And And these were not your normal 5 solar mass black holes. These were like 30 solar mass black holes, so more massive than you would find in X-ray binaries, for example. And by now, this is just, almost every day they can find black holes. Right? They have more than 50, but even larger binary black holes in the 3 catalogs that have been published by LIGO. They have also detected black hole neutron star mergers. And so our understanding of the compact object population, of course, has been revolutionized by LIGO. We have now a large sample of massive black holes from gravitational waves, slightly less massive black holes in binary systems that emit like X-ray binaries, for example. And even some neutron stars, as we'll see in a moment, from LIGO combined to all the electromagnetic neutron stars that we see before. Okay. So this is in the context of massive star explosions and transients. And so in the case of neutron star mergers, of course, you might have heard that they are also loud emitters in gravitational waves. And in contrast to binary black holes, because there is matter involved, there is also electromagnetic emission pretty much guaranteed to occur. Right? Maybe very short, but the fact that matter is involved means that some electromagnetic emission will be emitted, and if the conditions are good, a lot of electromagnetic emission will be emitted. And this is just a simulation from the Frankfurt group showing 2 neutron stars where you end up with a tidal tail being ejected, it's dynamical ejecta. Some of the material that is not unbound circularizes angular momentum of the binary and forms an accretion disk. Right? And then in this particular case, the 2 stars form a black hole shortly after merging, because the combined remnant exceeded the maximum mass of a neutron star with rotation and thermal energy. Okay? So neutron star mergers are very rich multi-messenger objects. So what we see here is a diagram showing us the overall timescales of the event, what's happening conceptually, and then the signal in gravitational waves and electromagnetic waves that we expect, right? So we have the in-spiral phase, which is where most of the gravitational wave signal seen by LIGO comes from. There's the actual coalescence, dynamical phase. Right after that, if there is a remnant that can survive, it undergoes post-merger oscillations that can be seen in gravitational waves if they are close enough. In part because the frequency is now kilohertz, and so LIGO is not as good as detecting this. This diagram should have this frequency much higher than that one, but that's what we drew, right? And then once the merger takes place, we have an accretion disk, and that's where things like short GRE emission in the X-rays and the gamma rays, and later, once the blast wave produced by this merger expands, we can have a thermal transient powered by the radioactive decay of heavy elements, caused by the name of kilonova, that can shine in principle in the UV, in the blue optical, red optical, and infrared. And ultimately, once this ejecta collides with the interstellar medium, generate a radio transient. Okay. And the last point on physics here is that neutron stars, of course, are neutron rich. The beta equilibrium condition in cold neutron stars give us only a few % protons and 90-something% neutrons. And so there's a lot of free neutrons, and once you have a medium with a high fraction of neutrons and hot and expanding quickly, you can allow the occurrence of what is called the rapid neutron capture microsynthesis process, in which neutrons are captured onto heavy seed nuclei. And this is efficient because they do not experience Coulomb repulsion. So one can quickly build up very neutron-rich, heavy nuclei. But those nuclei are unstable. The strong force does not like high asymmetries in the number of neutrons and protons, and so those decay by beta decay, turning neutrons into protons. So let's say that we have a neutron here that becomes a proton, and that radioactive decay generates energy locally because positrons or electrons, but positrons for the most part. Sorry, electrons, not positrons, are generated, and so that injects thermal energy locally, and that's the radioactive decay rate that we see from the R process. Okay, so this process, of course, is thought to occur in neutron star mergers and also in Corcola Supernova, although sophisticated models that include detailed treatment of neutrinos find that conditions are there, but not to produce the heaviest elements, because you need really neutron-rich conditions. It only tends to make the light R process elements, whereas neutron star mergers can easily go all the way to the third abundance peak. So this is abundance, and this is mass number. So there's third peaks having to do with the closed shells. Okay.
Sorry, Rodrigo.
Yes. Yeah.
But there's also now some research that shows that in principle also collapsars, even if not typical collapsing stars, but rather collapsars with accretion disks and something like that could produce like 100 of.
Yeah, that's a very speculative, but yeah. So I lumped them together with Corcola Supernova. So by Corcola Supernova, I don't just mean neutrino-driven supernova. So those are the ones that it's true that those, you're right, that those are the standard neutrino-driven supernova are the ones that are found to not be good at generating our third peak. But you're right that collapsars can, in principle, generate the conditions for neutron-rich outflows, right? And the hypothesis is that, show later on, right? When you have MHD evolution of the accretion disk, you have expansion on a timescale faster than the weak interaction rate, right? In many cases. And so for the collapsar case, it is thought that neutrino irradiation can turn the disk more neutron rich. So this is YE of 0.5, material collapsing from the massive star, and neutrino cooling lowers the electron fraction, and then the NHD just launches that material away, right? Because otherwise it doesn't deviate too much from YE of 0.5. The other possible place is magnetorotational supernova that have also been studied, and there what happens is that you have the iron core that collapses, and so again magnetic processes launch matter fast compared to the time the neutrinos take to change the composition. And so you can eject some neutron-rich material that allows you to get to the third R process peak. The one thing that magnetorotational supernova and collapsars share is that the rate is expected to be lower than run-of-the-mill neutrino-driven supernova. And so, yes, so in the case of collapsars, you're right. If the yield is, 50 solar masses, then that's a lot, even if the rate is low. And so the product of the rate and the yield can maybe compensate and be a competitive source compared to neutron star mergers. Yeah, that's a good point.
I have another question. So
yes.
With these new studies, like what are the new ballpark numbers that heavy elements are like more than 70% are through neutron star mergers and the rest is Corcola Supernova, or what?
Oh, I don't think that anybody has a precise number, because my understanding is that there's not just the yield per event, there's the rate, and there's also the mixing of the this is embodied simulations that people do when they inject our process, and then they see how the hydrodynamics of the ISM turbulence mixes things throughout. And so yes, you're right that from a galactic chemical evolution point of view, there's the issue of timescale. So collapsars and magnetorotational supernova and even standard Corcola supernova tend to happen quickly once a massive star forms. So early in the galaxy, if we have a massive stars, you will have some indication of our process taking place early, whereas neutron star mergers take a while. There's a quote-unquote delayed time, because you have to wait until the binary comes close by common envelope evolution or whatever, right? And so I don't think it's well established which ones of the two dominate. There are papers coming out either way, right? one problem that I have as a theorist is that we only have theoretical predictions for collapsars and magnetorotational supernova, and for neutron star mergers we have one data point, empirical data point, right? So we can do all kinds of simulations, but in the end, answering that question confidently requires that I think we have more data of events.
Okay. There's this dwarf galaxy of the Milky Way, Reticulum. I forget the phone number.
Reticulum 2. Reticulum 2.
Okay, so it was an easy phone number, but they found it that it's enriched, and it's unlikely that a neutron star could have merged, because those tend to have large velocities, and it would have left that galaxy, whereas a collapsar or an MRI supernova would be able to do the trick there. Right?
So they have small populations, and so maybe there was one burst of star formation, and as you say, even if there was a merger, it would have flown away. Yeah, those small galaxies I think are good kind of to test the concept whether you can, for example, in this case, have a collapsar kind of taking care of the abundant scene. But on a wider galaxy scale, I'm not sure we can either rule out or at this point, right, give more preference to one mechanism. So we know that neutron star mergers can, by themselves, do a significant fraction. Whether that's 70% or 50%, I don't think anybody can say at this stage. All right, so we kind of went back and forth, but basically the evidence for our process production in neutron star mergers is the W17 which show this kilonova transient, and the properties of that transient allows us to infer the ejected mass and the velocity, and whether the composition had light or heavier process elements, because that composition imprints itself on the opacity of the material. Okay? And so the fact that the transient, this is a spectral energy distribution as a function of time, so from half a day to about a week, right? So it changed from the blue UV to the near infrared in about a week. So that quick temperature evolution and sorry, is there a question? I missed it. So that quick evolution and the transition to the infrared is a signature of the presence of our process elements, and so that allows to infer how much our process mass was ejected. Right? So that's this quote unquote smoking gun for neutron star mergers. Okay, so that's kind of the broad overview, and now I'm going to just tell you a bit about what we do in our group at U Alberta. So again, we have this diagram showing you how the different electromagnetic counterparts are produced when neutron star mergers take place, and so we have these two accretion disks that eject mass, so the dynamic and ejecta. So my work has primarily focused on the evolution of the accretion disk and how that contributes to the kilonova transient. So there's been a long body of work on this topic, and there's even precursor work done, I believe, at UNAM on collapsar disks that are very close relatives of neutron star merger disks. In this case, it's just the disk. You don't have a confining round pressure, just the disk. And most of my initial work on this was doing hydro simulations in 2D using alpha viscosity, and crucially including the neutrino physics to allow both the heating and cooling of the disk and the evolution of the composition, so the YE, the electron fraction, so to speak, right? Because that tells you whether the ejecta is going to be blue or red once you map into opacity. There's a pretty good one-to-one mapping between electron fraction and opacity. Once you are above YE of about 0.25, you cannot make any heavier process elements, and so the kilonova looks pretty much like a regular supernova, blue. But if the YE is less than 0.5, then you make heavier process elements and you have this infrared transient. Right? So that's kind of the logical direction. So what we did in 2014 with Brian Metzger is look at what difference in the outflow does it make to have a hypermassive neutron star at the center versus a black hole. Same disk, same properties, same mass, but you just have a source of neutrinos from the center and this is the neutrino heating, you see that it's quite different, even though the viscous heating is not from the disk, is not that different. And this increase in neutrino irradiation by the central object means that the outflow, so this is now the electron fraction of the outflow, is quite different. And the signatures in terms of whether the kilonova is blue or red depend on how long does this hypermassive neutron star live. Like the longer it lives, the more blue the outflow, basically. That's the initial result. Now once, and this was pre-17017, it was 2014. So once 17017 came out, my student Stephen Feldman took the same simulation code and now asked the question, with the physics we have in, the alpha viscosity, the neutrino emission and absorption, and the variable neutron star lifetime, can we reproduce the inferred properties of the kilonova? So the observers watch the transient, and they say this can be fit with 2 components or maybe 3 components, and one is blue, one is red. And so we have the ejected mass and the velocity inferred from observations with some error bars, obviously. So this is the ejected mass and the velocity. The horizontal bars you see are the from the Villar. Where is Villar? Oh, we don't, the Ashley Villar paper, 2017, I think. This from the observations, and then the points are the velocities and ejecta that Stephen got trying to find whether we find any combination of parameters. And basically the result is that the ejecta mass can easily be produced by some combination of parameters. So a more massive but slower red neutron-rich component and a faster blue component, a high velocity, but less massive. The mass can be reproduced, but the velocity can't. Okay, in particular, the velocity of the high, the velocity of the blue component, which is something like 0.25 c. The energy is squared, so it's basically significantly higher. And the red component, fine, no problem, but the blue component cannot be reproduced with viscous hydrodynamics, no matter how bright you make the central neutron star. It's just neutrino absorption cannot give you sufficient energy for the outflow or viscous heating. You can increase the alpha parameter, it doesn't change, right? So the conclusion is viscous hydro cannot give you the blue kilonova component. So we also, before 17017, we knew that this was a significant effect, that the magnetic evolution of the disk is a crucial ingredient. And so we carried out MHD evolution of an accretion disk. This is using harm, pretty much like all the accretion disk, GRMHD accretion disk simulations that have been done before, but we added the neutrino physics in parametric form for the cooling, and we added nuclear recombination. So when neutrons and protons form alpha particles, that releases energy, and so that aids the outflow. So we added the nuclear recombination and the neutrinos, and we were slightly after Siegel and Mesker, who also did something similar to this. But we were able to evolve the simulations for a very long time. Okay, what you see here is
one quick. So
yes,
how important is your GR, or are you far enough that the GR is sort of negative?
Yes. So for the good question. So for the wind itself, it's there's 2 components of the wind, and I think you have a paper showing that too in the collapsar. Sense that once the weak interaction shut down, in this case, you have a relatively inefficient disk, and so that thermal outflow gets a kick from the alpha particle recombination, and that happens far from the black hole. And in that case, GR has completely no effect. But when it comes to adding MHD, the MHD itself adds another component to the outflow that's really momentum equation. The other one was energy equation, thermal, and for that you need the GR next to the black hole, because otherwise the velocities are not quite right. And furthermore, you get a jet once you add GR and MHD, and so there's an interface between the jet and the wind, right? That has a fast component, that if you want accurate predictions, without GR is not that good. If you remove the GR, so I'll tell later that one of my students is doing a pseudo-Newtonian GR.
Yeah, I was gonna say, like in this study you're showing that you use Paczynski beta or something like that, and do you see, did it change?
Yes. Here I use Paczynski beta for the black hole. So one of my students, as I'll say in a moment, is doing a pseudo-Newtonian spinning black hole. It's Artemova potential with MHD in 3D, and we do get the wind even to 0.25 C, but we don't get a jet, obviously, because you need the what is it called? I forgot the rotating space-time around the black hole to get the jet, right? The Blandfors-Naik mechanism. Right?
Oh,
and so, so these simulations don't have neutrino heat. That's the one caveat. But go ahead. Yes.
Sorry. So you include Blandfors-Naik, and are you also including Blandfors-Payne, or is it only from the rotation of the black hole?
So the GR-MHD simulations, you just solve the MHD equations with a Kerr metric.
Okay.
And these mechanisms arise from the physics, so you don't have to put anything by hand.
All right.
So, but yeah, you're right that the Blandfors-Naik relies on the rotation of the spacetime, and so the Kerr metric takes care of that.
Mm-hmm.
And this code, Harm, is written such that it's a coordinate system that goes through the horizon. And then is mapped into spherical coordinates for data analysis. But in those coordinate systems, we have the full rotation of the spacetime and everything.
Okay.
But the new part here is that we added the evolution of YE with the weak interactions and the nuclear recombination, and we get essentially when we compare with hydro. So this is GR-MHD and this is alpha 0.01, 0.03, 0.1, right? We get the same late time evolution. So that's the wind that I was talking about before, the thermal wind, where alpha particles have a role to play. That's the same at late times in the MHD simulation. So that's the black curve and the color curves for different alphas. But then the MHD simulation has a lot more emission at early times. And this is the Lorentz force just kicking stuff out on an orbital time. Right? And that is essentially has factor 2 more mass ejection compared to hydro in MHD. So just to give you a table, of course, those of you who have done MHD know that the initial field geometry you put in is crucial. And so what we have here is on top a comparison of a GR-MHD simulations from 2 papers, one that I led and one that Christy et al., Sasha Tchaikovsky's group led, in which we have GR-MHD models with initial field geometry. So this is strong poloidal, weak poloidal, and toroidal, right? And then hydro simulations like the ones I showed you before with different values of the alpha viscosity parameter. And essentially it's a monotonic relation first of the fraction of the disk ejected. So this is percentage, right? So 16% for alpha 0.01 going up to 22 alpha 0.1. And then you go to MHD, you go from 27 toroidal field up to 40% for strong poloidal field. Okay, so there's a monotonic relation between the strength of the initial poloidal field and the fraction of the disk ejected. And also the average velocity. So the outflow gets faster as you add more poloidal field in the initial configuration. Okay. So that's kind of the main part of adding MHD to the black hole case that we found. Of course, as I said before, my student Stephen Fallman is doing flash simulations with a pseudo-Newtonian potential, but now better neutrino physics, neutrino leakage for emission and absorption. And the GR-MHD simulations only have emission. And doing absorption is slightly more complicated because you have to irradiate the disk, and so you need to put in the geometry and calculate the global luminosity. The cooling is only local, right? You just compute the cooling rate and that's it. And so, yeah, we just submitted the paper, and it should be coming out hopefully in a month or 2. Mostly notices. Okay, so yes, another aspect of this is that the thermal transient, the kilonova, can have early. There's a question in the chat. Okay.
No, Rosa is telling us nicely to Enrique and me to shut up.
Oh yeah, okay, all right. The other aspect of the transient is that there can be this is predicted, right? This has never been seen. There can be a neutron precursor, or neutron powered precursor to the kilonova. So this was seen. There was a blue kilonova and a red kilonova, powered by radioactive decay of our process elements, and this is a prediction. When this binary neutron star, when the two neutron stars touch initially, there's a early ejecta from the contact interface that is very fast, meaning that compared to the ejecta that comes later. So the ejecta later is 0.1, 0.2 C. The ejecta from the disk can be 0.05 C. This fast ejecta can be more than 0.5 C, right? But it's a very small amount of mass going very fast ahead of everything. And when that happens, when you have very fast ejecta, it means that the expansion time of matter is fast enough that our process freezes out. Right? So those neutrons that were supposed to be absorbed into heavy nuclei, eventually the collision time becomes slow compared to the expansion time, and so the free neutrons are frozen out. Right? But as you know, free neutrons are not stable; they decay, beta decay into protons and electrons and antineutrinos, and that if they're in a fluid, that energy is released. Right? And so the prediction is that there can be a neutron decay powered precursor to the kilonova shining in the ultraviolet. Why ultraviolet? Because it's a very thin layer, so it's very hot, and so the thermal emission is in the UV. Right? However, people who have studied this fast ejecta using both grid methods and SPH methods, so this is hydrodynamics using smooth particle hydrodynamics or grid-based, find predictions that are different by a factor of 100. Right? And so there's a lot of uncertainty. And so if one wants to predict the luminosity of a transient and there's an uncertainty by a factor of 100, it's hard to tell the observers, hey, look at that and integrate for this time. So we need to have a better handle on the amount of mass ejected in this little layer. So my student Cole Maldin and I designed a numerical experiment to ask the question, if we use a grid code and we can increase the resolution as much as we want, is there a convergence? Is there a resolution we need to say, now we trust this little amount of ejecta that we see ahead? And so we basically carried out a neutron star merger simulation in 2D. So we switched to a co-rotating frame, we add the inertial forces and some schematic effect of gravitational wave decay so that the stars collide. And so because it's 2D, now we can increase the resolution to meters, right? So the radius of a neutron star is 12, 13 kilometers, and we had resolutions that went all the way back to 4 meters, right? So that's 1 part in 1,000 or less of a neutron star. And so the main result is that the change in the ejected mass with velocity more than 0.6 c is less than 10% in basically the change in the ejecta, so that's the convergence, less than 10% with a resolution of 20 meters. So if you do a grid simulation and your resolution is 20 meters or less, you should trust your ejecta to within 10%. And that's the luminosity, roughly, of the UV transient accurate to within 10%. Okay. And if we extrapolate that to existing 3D simulations that are not too far from this, so the best resolutions out there are of the order of 100, 150 meters. They're not that far. And so we should be able to detect. Go ahead.
Yeah, so when you do 2D supernovae, you get all these troubles with convection and whatnot.
Yes.
So you don't really trust those simulations very much. So yes. Here you have very nice resolution, but
yes.
I would imagine that in a sense you could have similar problem to what you get with supernova. So yes, how much can you really trust it?
Yeah, so that's a good point. So in Corcola Supernova, the reason you get different results is that the turbulence is crucial to tilt the balance in favor or against explosion. And so So in supernova, the shock is stalled, right? And so you have a situation balance between the run pressure of the collapsing core and the thermal pressure of the shock. And so it's right there at the balance. So any little push you give it is going to set the explosion off. And so the turbulence behind the shock makes the neutrino energy absorption more efficient, right? And so, but that occurs over an extended period of time. So many dynamical times that the shock is stalled and turning and eventually gets accelerated. So the turbulence is a crucial ingredient in getting the shock moving, right? Here, we're just thinking about a ballistic collision in which you crash the two things and there's a blast wave going on. And so there's no, so turbulence is not dynamically important here. So it's just literally just raw hydrodynamic forces, gravity and the hydro, right? So I wouldn't worry about turbulence. And I think this is roughly okay for the contact ejecta. So the main vulnerability but I would say the main assumption that is violated here is the fact that in a 3D merger, you have a non-axisymmetric collision, and then you have a pulsation of the remnant. So they get close, and then they bounce, and then they collide again, and that bounce ejects material along the equatorial plane, but not like a disk, but like two tidal tails, right? And that component we don't have here. So the equatorial fast ejecta that comes from the first bounce after if you notice here, we have a bounce, but along the equator, so this is the rotational axis, we don't have a lot of ejection here. And it comes back because it's bound, right? It's not unbound. So the contact plane ejecta is reasonably well captured, but the equatorial bounce we don't get.
Okay, so it's a good experiment just to catch what's the actual fraction of these fast.
Yes. So what I would say, we are not showing you how much, right? It's explicit purposes. I'm not telling you, oh, it's 10 to the minus 4, solar mass is 10 to the minus 3, because that number we don't trust at all.
Okay. All right.
But we want to know is the difference, right? By how much it changes once we get the resolution right. And so that number, whatever it is, we don't trust it within a factor of 10, right? Does not change by more than 10% if you get a resolution of 20 meters, right? And so the relevant scale here is the pressure scale height in the star. Right? And so as you move closer to the surface of the neutron star, the scale height gets smaller and smaller. And so it's really what fraction of the surface layers of the stars you're resolving when you have this collision that determines how accurate is your first wave of mass ejection. Right? So that's kind of the way we understand it. And of course, we don't trust the absolute number because, as I said before, we're missing the equatorial ejecta and even the gravitational wave prescription we have is relatively simple. Right? But this result we think is reasonable. Okay, so I think I have 5 minutes to briefly talk about black hole formation in failed supernova. So we said that we have a...
Rodrigo,
yes.
No, pero no te preocupes por el tiempo. Tú dale. Estamos súper entretenidos con tu charla, entonces no te preocupes por el tiempo.
Okay, gracias. We started like at 11:05, so 12:05 Mexico time. So I was trying to hit but I think in 5-10 minutes I should be done. Yes, okay. So Corcola Supernova will go back to massive stars exploding. We said that once the central regions reach nuclear density, you have a proto-neutron star, and there's a stalled shock, right? And if the neutrinos or rotation or anything else manages to get the shock going, you have a successful supernova and the neutron star at the center. Right? Now, if the successful supernova leaves some matter bound, some of it can fall back and till the neutron star above its maximum mass and make a black hole. That's called a fallback supernova. Or the shock may never be revived because there's not enough neutrino absorption, or the accretion rate from the stellar core is so high that the shock can never get going. And then once sufficient matter has been accreted, reach the maximum mass, and that's it. A black hole forms. Okay. Now, collapsers have been mentioned before. If there's sufficient rotation by the right amount in the star, then the matter that is collapsing can circularize due to centrifugal forces. So angular momentum is conserved, so the distance from the axis times the velocity is conserved. And so if you decrease the distance from the rotation axis, the rotational velocity increases, and at some point, depending on the angular momentum value and the mass enclosed, that centrifugal force can be enough to resist gravity, and you have an accretion disk forming, and then very interesting phenomenology can ensue. And work at UNAM in the past have substantially explored that collapsar case, so I don't need to tell you. That's very interesting. But if there's little rotation or no rotation, the naive expectation is that you have a black hole that is a vacuum cleaner that just takes away all the star, and that's it. Right? In the absence of rotation. Right? But in the 80s, Nadeoshin realized that that's not the end of the story, because at least for stars less massive than about 140 solar masses, black hole formation is always preceded by a proto-neutron star phase. You always have a proto-neutron star that emits neutrinos, and those neutrinos carry away mass energy. Right? This is relativistic conversion of mass into energy. And so that generates a difference between the baryonic mass and the gravitational mass. So the baryonic mass is just the sum of the masses of all the baryons, neutrons, and protons. So it's just the amount of matter in there. Whereas the gravitational mass comes from the stress energy tensor in general relativity. And so it also includes not just the rest mass, but the energy, right? And so the gravitational mass becomes smaller than the baryonic mass by a little bit, right? But that little bit is such that the outer layers of the stars feel a change in the acceleration of gravity. Right? Gravity is set by the gravitational mass, not the baryonic mass. And so the outer layers that were in hydrostatic equilibrium with the old gravitational mass equals baryonic mass, now they're no longer in hydrostatic equilibrium with the new gravitational mass that is now lower. Right? So gravity is lower. The pressure gradient was balancing a stronger gravity, and now gravity got weaker. And so the pressure gradient results in some matter being expelled from the star. Right? Now, where in the star is this important? Basically, you can imagine a radius in which the free fall time, this is the local time for gravity to act, the dynamical time, is comparable to the neutrino cooling time. But this is the time over which the proto-neutrons are cooled before becoming a black hole, and the time over which this difference between baryonic and gravitational mass grows and establishes itself. So that's the relevant timescale. If that timescale is slow compared to the dynamical time, the local fluid element that's collapsing is going to still go to the black hole. So this is the case. They're close enough to the black hole. The free fall time is increasing as you move out. Basically, if the free fall time is faster than the neutrino cooling time, the element just falls in. But if the free fall time is much longer than the neutrino cooling time, then the change in the mass is instantaneous. And the layers in the star feel an instantaneous decrease in the gravity, and boom, there's a transient, right? A mass ejection, essentially. So that's the essence of the mechanism. Now you can estimate, just with some order of magnitude, what the energy of that pulse should be. So basically, it's the change in the gravity due to the change in gravitational mass times the free fall time. So that's the impulse. Right? So there's a little impulse because the gravity changed. And with that velocity and the mass of the shell, it's just the pressure scale height times the radius, 4 pi radius squared, one can get a kinetic energy of the pulse, and that's of the order of 10 to the 47, 10 to the 48 erg. Right? So immediately one knows that the energy scale is 3 or 4 orders of magnitude smaller than regular supernova, which is 10 to the 51 ergs. Right? So this is a very weak, puny transient, but it's observable. That's the whole point. This just tells us how the energy distribution looks like inside the star. Importantly, this is important to understand what comes next. How much mass is ejected by this puny energy injection depends on how tightly bound the outer layers of the stars are. right? So basically what happens is that the star will eject the outermost shells that have a binding energy equal to the energy they're injecting, right? So what this is yes.
Sorry to bug you again. So for a typical supernova, you have 10 to 51, but that's the kinetic energy, right? So in terms of luminosity, it's 10 to the 49, which is not that far away from this. Now, this is, of course, I guess, only kinetic energy that you're injecting here.
Yes,
so,
yes.
but you're in the region where the opacity is very low. So you could probably get a large amount of that kinetic energy converted, or not.
Yeah, so I'll get to that point where we estimate the luminosities of the. So there's two sources. One is a shock breakout. Once you have if you get a shock, because sometimes you don't get a shock, but if you get a shock, you have the photons trapped inside the star bursting out quickly. That's shock breakout, and then you have so-called plateau emission, which is the standard, blast wave expanding and the photosphere recombining, and you have a little transient. And so you can get the luminosity from both of those mechanisms, and it depends on how much mass is ejected and the velocity of the shock, and that can change drastically. All right. So let me explain this first, and I'll get to that
Thanks.
part, the electromagnetic counterpart, when we finish. I think I'm over time already, but I'll try to be fast here. So the important point here is that if you look at the exterior binding energy, so you start from the outside of the star and you count mass and binding energy. So we go from the outside in. We see that there's roughly 3 classes of massive stars: pre-supernova, red supergiants, blue supergiants, and Wolf-Rayet. Wolf-Rayet are very compact. They ejected most of their mass by winds. Red supergiants are convective, puffy, and big, right? And so basically, a binding energy of 10 to the 48, 10 to the 47, one can ask how much mass is exterior to that binding energy. And for red supergiants, that's about several solar masses of very weakly bound convective envelope. For a blue supergiant, it's something like 0.1 solar masses, and for a Wolf-Rayet star is like less than 1% of a solar mass. Right? So that's the amount of mass that is ejected by this pulse. Okay? And so there had been work by Lovgren and Goosley before looking at red supergiants, and they found that you can eject several solar masses, but the transient would have a luminosity, going back to the question, of 10 to the 39 ergs per second, peak luminosity, and last for about a year and be in the near infrared. Right? And this is the shock breakout that I was talking about before. In parallel to this, the Ohio State group had started a survey looking for disappearing massive stars. So they monitor a whole bunch of red supergiants regularly, and they look for stars that disappear, meaning that they underwent a failed supernova and a black hole has to be there, right? And they found one candidate in 2017. I think there's another one reported last year that I don't have here, but basically they had a red supergiant that was just shining happily, and then had a bump, and then it went off. This is basically the background noise of the photometry, right? So it basically it kept shining in the infrared, and that's kind of an unsolved, unexplained part of it. But basically, the red supergiant that was there had a bump that lasted for a year, and then it went off, disappeared. Right? So this is essentially the first, and they went back to observe it recently, and it's just not there. Right? It's the first case in which we think we have a failed supernova candidate, and so they call it name of the galaxy BH1, so black hole 1, which is consistent. The properties are consistent with this prediction for the red supergiant for this mechanism. Now we ask the question: okay, red supergiants are fine, but what about blue supergiants and Wolf-Rayet? So short story, we basically reproduced their approach. Basically, you have a point mass at the center, you change the gravity, you see what happens outside. We did the simulations on Flash, and we extended it to other progenitors that had not been seen before. And we find, to make the story short, that this mechanism operates in all kinds of stars. So this velocity, Mach number, density, and temperature, this is radius, and the different color curves at different instants, right? So in all cases, you see that a shock forms and moves out of the star. Depending on the envelope properties, it can slow down, it can accelerate. There's an old paper by Stan Woosley that even relies on work by Sakurai that tells you that the slope of the density gradient determines whether the shock accelerates or decelerates. And so that's what sets basically the final velocity when you reach the stellar surface, is the dashed line. But unsurprisingly, the more compact the star is, the faster the shock moves out. For a red supergiant, we have a shock moving at 100 kilometers per second. For a blue supergiant, it can move a few thousand kilometers per second. And for the Wolf-Rayet, it's tens of thousands of kilometers per second. Of course, the mass is very small. My student Mario Ivanov extended this work by computing the inner evolution of the core with GR1D. So no longer a parametric change in the gravitational mass, but actually using a neutrino transport code in GR to get the difference between gravitational and baryonic mass. And then we plug that into Flash and we see how things change. We find the same trends we found before. So the energy ejected is inversely proportional to the compactness of the core of the star, so how centrally concentrated mass is. And the ejected mass depends on the plot I showed you before, how tightly bound the outer layers of the stars are. So if the envelope is very compact, you eject very little mass, like a Wolf-Rayet case. If it's very puffy, then you can eject several solar masses. Right? It's the red supergiant case. Now, going to the question of electromagnetic counterparts, there are analytic formulae one can use to estimate the shock breakout luminosity and the peak luminosity and duration of the plateau phase. So for red supergiants, we have luminosities of order 10 to the 6 solar luminosity, so that's 10 to the 39 ergs per second. It gets much more luminous, the shock breakout, once you go to blue supergiants or red supergiants, but shorter, right? So hours or even seconds. This is the plateau luminosity. In one case, we found that there's no unbound mass if the equation of state is soft. If the equation of state is stiff, then you do get some unbound mass, and that has to do with the fact that black hole formation and therefore neutrino cooling time is longer for stiffer equations of state, and so you can make a bigger difference between baryonic and gravitational masses for stiffer equations of state. But the plateau luminosity for the blue supergiant is quite interesting. So it's about 20 days, 8,000 Kelvin, and it can last for about 20 days, and 2 times 10 to the 6 solar luminosity is 10 to the 38 ergs per second. So it's a faint transient that lasts for 30 days, and it's in the optical, right, or blue optical. Right? And the expansion velocity is about 600 kilometers per second. So this is consistent with what we had found before with parametric evolution of the core. But now we can say, if the equation of state is stiff or soft, then we get this different transients. Okay? So that's everything. Just I'll leave my summary here. I overshot by like 10 minutes, but hopefully that's okay. And thank you very much. If you have questions, I'm happy to answer them.
Okay, thanks, Rodrigo, for the talk. Let's keep talking in English because we have a student of Rodrigo here. And if you have questions, please raise your hand. Okay, Fabio.
Thank you, Rodrigo. I have 2 questions. So the first one is, what is the rate of these supernovae? Well, failed supernovae.
The failed supernovae?
Yeah.
I think that the number has changed recently, but the one I remember from 2017 or 18 is about 1 in 7.
Wow, so very frequent. Okay.
Yeah, so this survey, I forgot if it was volume limited or magnitude limited. Within a certain period of time, they found 7 supernovas, so 7 of the red supergiants exploded and 1 disappeared.
Wow. Okay.
So this is within red supergiants.
And the other one, when you were talking about the fastest ejecta.
That it's never been how to say. It's not that it has never been seen. It might have been seen, but people don't know what it is. It's never been confirmed like this one, in that we know there was a red supergiant and then it was gone. So this is confirmed. The other ones, basically, the utility we see is that we're telling observers, if you see something like this, usually these things get discarded because people say, oh, we don't know what it is, unknown transient. Now we're telling observers, this is one possible explanation. So for a time, the people studying the cow supernova were kind of interested in the blue supergiant scenario, but I think there's some high velocities in there that are inconsistent with what we find here.
But the cow is very luminous, no?
Yeah. So yeah, it could not be. It could not be this, I think. But that kind of unusual supernova that is short and bright and so on. For instance, people have thought that maybe you have this first pulse from this, and then you have a jet punching through it, and all kinds of variations we can think of.
Yeah. And the other question is about the previous part of the talk. So when you were talking about the fastest ejecta, and you showed a schematic representation of it. So can you go back to it, please? Yeah, this one. So where is the GRB? So the GRB is the region, the blue region will be larger than 0.c, or is a different component?
Oh, it's a different component. So this is not the jet yet. So this is the dynamical ejecta.
Okay.
So it's you would call it the slow ejecta compared to the jet. And so the assumption is that, this happens immediately upon contact, right? To get the jet going, you need at least some disk forming, and that takes, 10 milliseconds or so until the metric settles and you have a disk going on. And once the disk is in place, it takes, 5 to 10 milliseconds to get the jet going. And so I think how I see it is that you have this splash of ejecta going out, and then the jet punches through. And then you have the issue of, is there a cocoon or no cocoon? And the jet was able to punch through it, and the medium the jet punches through is this. Right?
Okay, thank you.
More questions? Rosa?
Yes, maybe it's a light question, but could you go to the slide when you mentioned the blue and red kilonova parts? No.
This one?
No. The sketch. I think.
Yes.
Yes.
Okay.
What is the neutron precursor? I never heard about this before.
Yes. So it's a prediction. So it's not been seen. And part of the reason is that for 17017, GW17017, there was a delay of 10 hours between the gravitational wave signal and the GRB, and the time the first optical observations were taken. So 10 hours passed, and then we got the blue kilonova. Right? So I think it could have been seen had we been observing right away, like an hour later. But since this is the only event we have seen, right? We don't know if it was there, right? But it has been predicted, and it had been predicted in 2015. So this paper I was referring to from Brian Metzger and collaborators, which we base our hypothesis on, had predicted this scenario, and of course the luminosity will depend on how much mass is ejected in this blue layer here, the forward part of the ejecta. And the main problem is that nobody knows for sure if it's 10 to the minus 6, 10 to the minus 4 solar masses or 10 to the minus 8 solar masses, right? So it varies quite a lot. So yeah, it's a prediction at the moment.
Okay, thank you.
Okay, I think that we don't have more questions.
I have one another.
Here,
Aldo. I was waiting for someone else. But about the neutrino-induced supernovas, the one that the failed explosions.
Yes.
So to produce them, I have played with them a little bit. The one that does not include the neutrino production and everything, the 1D neutrino production, the ones before, you just remove the mass and you get the change in the gravitational energy, right? And then everything works out.
Yes, so you're right. It's a pure hydro simulation in which we assume that the black hole formed, right? So the first generation of models, we just basically took the prescription of Lagrange. We cut out 2,000 kilometers, that's like the size of the iron core, and we just turn that into a point mass. So the mass in the domain is the point mass plus the enclosed gravity. And so then we just use these equations to just turn it into a black hole. With GR1D, we basically do two separate simulations. Right? In one case, we evolve this to a black hole, right? So we have a history of how the two masses started to differ, and then we use that time history in Flash, like a prescription for how the point masses vary.
Okay.
Yeah, it was still an open boundary as a point mass, but now we were telling Flash, okay, this is the gravity change over time.
Nice.
But it's no full-scale Corcola Supernova simulation.
Yeah. I was just wondering how you dealt with the energy change in this.
So this is I would say the state of the art in the field, because we actually use a GR code to get this mass difference. But of course, a full self-consistent supernova simulation would be even better. The thing is that those simulations have a hard time evolving past 1 second, right? In 2D or even in 3D. In 3D, they can hardly get to 1 second, right? And so here we start only with 4 seconds, but these things, right, go to 10 to the 7 seconds, right? So so
it's a large range of time.
So we can do that, and this is kind of a technical point for those of you who do simulations, is that we can do that because if you notice the velocity, it goes very quickly to negative, right? Because it's collapsing on the black hole, so it's very highly supersonic going inward. And so once the flow is supersonic, it's causally disconnected, so we just move the outer boundary out with time, right? You can see that here. And then the time step gets bigger and bigger, so you can get all the way to like 10 to the 7 seconds, right? So that's the trick.
Nice. Thank you.
Yep.
Okay.